Swayam Prabha. Digital India. Educated India.
So, do you guys remember what we were discussing yesterday? What were we discussing? So, we were discussing about the importance of enzymes and why is it important to study enzyme kinetics, right? So, basically, so what did we, so our basic assumption was E plus S is in equilibrium with ES, which gives E plus P. So, we are neglecting the backward step of this, right? And so, we ended up with a mathematical expression. Does anybody remember rate of, so is this called rate or initial rate? So, you should remember that whatever we have derived is for initial rate, right? So, initial rate is equals to, what did we come up with? Vmax into concentration of substrate by Km plus concentration of substrate. So, this is called as Michaelis-Menten equation, right? And we also did a linear plot of that, which is called Lineweaver-Burke plot, which makes our life simple, which is 1 by nu is equals to Km by Vmax into 1 by S plus 1 by Vmax. So, this is it's called Lineweaver-Burke plot, which is basically, this is a what kind of graph or what kind of mathematical expression is this? What is the nature of the what is the nature of the curve? This is a rectangular hyperbola, right? Whereas this one is a linear curve. So, we made our life simple by converting a rectangular hyperbola into a linear curve. And do you remember what are all these things that are giving? What is Vmax? What is Vmax? Maximal rate the enzyme can obtain, right? So, this is a maximum rate of the reaction that an enzyme can obtain. And what is Km? What is Km? Michaelis-Menten constant, and what information does it give you? So, it is a concentration at which you have half maximal rate, but is actually what it is giving you is the binding between the enzyme and substrate. So, it is basically telling you about this particular step where the enzyme binds to the substrate. So, your Km has to be low or high. So, so that means you need to have a low, if you have a lower substrate concentration that can form this complex, that is more efficient, whereas Vmax has to be a higher value, right. So, at a low substrate concentrations, what is the order of the reaction? At a low substrate concentrations, what is the order of the reaction? First order, because it will be basically this, right. So, it will be a first order, and at a high substrate concentration, all this will go, it is basically V nu is equals to Vmax. So, it will be a zero order reaction. So, you will have a fractional order between these two, right. Can you tell me at what substrate concentration will you get Vmax value? So basically your nu is the rate of the reaction, Vmax is the maximal rate. At what substrate concentration will you get Vmax value? At what substrate concentration will you get a Vmax? So, nu is the rate of the reaction, right? So, at what substrate concentration will my rate of the reaction be equals to Vmax? When substrate is 1? At what substrate? So, you did at a low substrate concentration, you will have a very low nu, right? At a high substrate concentration, you are saying it is a zero order reaction. Now, half of what? When substrate concentration is half of what? Half of Vmax. Vmax is the rate, no? It is not a concentration. Vmax, what is the unit of Vmax? What is the unit of Vmax? Vmax is what? Rate, right? What is the unit of rate? Rate of a reaction. How do you, what is the rate, units of rate of a reaction? Second inverse, right? So, you need to have a second inverse there. So, this is also rate of the reaction, this is also rate of the reaction. So, your Vmax units is second inverse. And what are the units of Km? What are the units of Km? Molar, not mole, molar, right? Okay, now my question is, at what substrate concentration will my rate of the reaction be equal to the, this is the highest possible rate, right? Vmax is the highest possible rate. Now, my question is, at some point will my rate of the reaction, this is the highest possible rate. So, at what substrate concentration will my rate of the reaction be equals to Vmax? Your concentration cannot be rate, no? 1 by infinity or infinity. Okay, forget about it. Now think about this mathematical expression. At what substrate concentration will these two be equal? When will my V equals nu is equals to Vmax at what substrate concentration? This is also substrate concentration. This is also a concentration. This is also concentration. So at what concentration will my mu is equals to Vmax? When Km is equals to 0, right? So Km is equals to 0 means this is actually not, it only have Km, what is Km? Km is basically telling you the affinity between these two, right? Lower Km means it's basically a very tight binding. Km 0 doesn't mean anything. So Km 0 means, that means there is, the interaction is basically a covalent interaction kind of thing. So there is no, the interaction is so high that even a 0 concentration you are forming this. So Km 0 doesn't make any sense. There is no meaning of Km is equals to 0, right? So Km is never going to be 0. So that means your nu is never going to be Vmax. So Vmax is only a theoretical value. You can never get it experimentally. So what I am trying to tell you is Vmax is the limit. When you say limit extends to infinity or something, right? You are never going to that value infinity. So here also the Vmax is the maximal theoretical value that is possible. In experiments, you will never get V is equals to Vmax. You are only going to get the rates that are closest possible to the Vmax. Okay. If this is a very small number, for example, if your Km is nanomolar, right? If this Km is nanomolar, this will be 10 power minus 9 molar plus your substrate concentration by substrate concentration. Now, if you have a substrate concentration of micromolar, then you can ignore this. You are only approximating it so that your nu is equals to Vmax. But under no experimental conditions, your rate of the reaction will be equals to Vmax. Okay. So that is something that you should understand, is it's only a theoretical value. Vmax is only a theoretical value, whereas Km is an experimental value. You can get exact Km for everything, but Vmax you are only getting by extrapolating it, but experimentally you will never get at any substrate concentration. You will not get nu is equals to Vmax. Okay. So this is a Michaelis-Menten kinetics, but this is not the only kind of kinetics that is there. Enzyme kinetics can also be more complex. There is something called, does anybody know what is the shape of the curve? Do you know what is the shape of this curve? This is a sigmoidal curve, right? So there is no rate at all in the beginning, and then there is a sudden change, and then the rate saturates. Okay. So this is called Michaelis-Menten kinetics. This is called sigmoidal kinetics, and this kind of kinetics is also observed for enzymes that are having allostery. Does anybody know here what is allostery? Have you heard of the word allostery? So generally you have one enzyme, one substrate. So basically you have enzyme, substrate. But if binding of one substrate creates activity of more, so basically that means, suppose if it is not linear, right? So till a certain number of substrates are bound, there is no change in the rate. But once a certain number of substrates are bound, everything gets active. That means binding of one will influence the activity of the other. Or for example, hemoglobin. You have heard of an enzyme called protein called hemoglobin. So it is an allosteric enzyme. So hemoglobin binds to what? Huh? Iron is a metal, but what is the substrate that it binds to? It carries oxygen. It binds to oxygen, right? So binding of one oxygen helps it to bind more oxygens. So that means binding of one will improve it to bind more molecules, right? This is called allostery, where there is an influence of one substrate binding on binding of other things. So this is called allosteric mechanism. Okay, when the enzyme is allosteric in nature, then it will have a sigmoidal nature. So we are not going to talk in detail about this one. we have only talked about Michaelis-Menten kinetics, but this is not the only kinetics. You can also observe something like this. It's the same nu versus S, but you observe this when the enzyme is behaving in an allosteric manner. That means when one substrate affects the binding of other substrates. So when one substrate binds to the enzyme's ability to bind more substrates increases. So that is when you will see this kind of behavior. This is called sigmoidal. Okay. So we will not talk about that, but you should just keep in mind that this kind of behavior also exists. Okay. Okay. So now let us move on to the second topic that or the continuation of this topic, which is so we will move on to the next part of enzyme kinetics, which is called enzyme inhibition kinetics. Okay. Does anybody know what is enzyme inhibition? So any molecule that reduces the activity of enzyme, right? That is called inhibitor. Inhibitor means anything that reduces the activity, right? So enzyme inhibitors in enzyme inhibition kinetics means molecules that reduce the activity of enzymes. So inhibitors means molecules that reduce the activity of enzymes. So inhibitors means molecules or moieties that reduce the activity of enzymes. Now, why is it important to study enzyme inhibition kinetics? So, yesterday we have discussed why it is important to understand enzyme kinetics, but why do you think it is important to understand enzyme inhibition kinetics? Are you aware of any inhibitors? What are they? Vitamins, iron oxide. Iron oxide is an inhibitor for what? Okay. So inhibitors means, as I said, they reduce the enzyme activity, right? So yesterday we just discussed. So any drug molecules that you take are supposed to, if you are taking, for example, what is the common blood pressure drug? The blood pressure drug that you take is nothing but ACE inhibitor. ACE is the enzyme. So anything that reduces the activity of enzyme, this ACE is called ACE inhibitor. So it reduces the activity of it. So most of the drug molecules, you take the examples of antibiotics like penicillin, okay, or even if you take ibuprofen, aspirin, okay, even cancer drugs like methotrexate. All these molecules are inhibitors of enzymes. Okay, that means they reduce the activity of a specific enzyme. Okay, so if you want to develop or design a drug, right, you need to, and if you want, so any disease is because a certain enzymatic pathway is probably being more active than what it is necessary, or it is basically a wrong enzymatic pathway, right. Now, if you want to reduce the activity of that particular enzyme, then you need to design molecules that will actually bind to it better than the substrate, right, so that the activity is slightly going to be reduced of that enzyme. So most of the drug molecules that you see today are all, for example, the drug molecules that you take for BP are ACE inhibitors, okay. Penicillin is an inhibitor, okay. Ibuprofen is an enzyme inhibitor. All these are enzyme inhibitors. So did you read anything about medicinal chemistry? Do you have any experience of looking at drugs and how do they you're all doing first year chemistry, right? So how do you know how drug action is? Drug is not something you make molecule and you take it and it will work. No, you need to study a mechanism of action, right? Biological response is the response of it, but first you need to identify what kind of enzymes it is affecting, right? So as I said, lot of enzymes, lot of drugs that are there in the market are actually enzyme inhibitors. So if you want to develop a drug, then you need to study its kinetics, because the kinetics of it, that means what is Km giving you? Km is going to give you the effective binding of the substrate with the enzyme. Now if you are developing a drug that should have a better binding to the enzyme than the original substrate, right? Only then it will reduce it, right? So that means it needs to have what, lower Km or higher Km? It needs to have lower Km. So basically that means for understanding the Km as well as the Vmax, and you want to reduce the activity of it. Reduce the activity of enzyme is you have to reduce the Vmax of the enzyme. So you need to look for drug molecules that will reduce the Km or reduce the Vmax or do both, right? So so basically if you look at the molecules, as I said, examples of it, so any drug molecule that you look at are enzyme inhibitors. So how do they act? So suppose the enzyme, so I'm just, we'll do the kinetics or maths of it and then we will try to understand the, how to look at the, suppose you have an inhibitor I, right? So this inhibitor I can either bind to your enzyme directly or it can bind to the enzyme substrate complex. Okay, if it binds to EI, it will form EI. Okay, it forms ES, it forms ESI. Okay, I'm just taking an example of, so yesterday you saw the enzymes and the enzyme substrate complexes, right? So I'm just taking an example for taking, I have a molecule I. For example, ibuprofen, right? Ibuprofen is an inhibitor, right? It binds to the enzyme and it replaces the substrate. Or methotrexate. Methotrexate is a drug molecule that actually binds or replaces dihydrofolate in dihydrofolate reductase. So there is an enzyme called DHFR. Okay, the substrate for this is dihydrofolate. Now this particular enzyme is very, very important in base synthesis like purine bases, pyrimidine bases. You know the bases, right? Purine and pyrimidine, these are backbones of your DNA, right? There are 4 bases in DNA, right? Four bases in DNA, A, T, G, C. So they can be classified into purine bases or pyrimidine bases, right? So this enzyme is very important in basically synthesis of those purine and pyrimidine bases. Now the substrate for this is dihydrofolate. Okay, and if there is if you take a cancer, right? What is cancer? Cancer is there is an overgrowth of cells, right? Cancer is nothing but overgrowth of cells. So how do you reduce the I'm simplifying the entire picture, not giving the biological text, but cancer is nothing but overgrowth of cells. If you want to reduce the cell growth, anything that happens in the cell is because it starts from the DNA level, right? So now if you can reduce the synthesis of these bases, then you can actually reduce the growth of these cells and finally they can act as drugs for controlling the cancer. Now this DHFR enzyme is a very, very important component that binds to dihydrofolate. This enzyme is important for synthesis of the bases like purine or pyrimidine. Okay, now if you want to reduce the activity of this enzyme, because the substrate is dihydrofolate, now you can add an inhibitor where the enzyme is going to bind, so the inhibitor is methotrexate. Okay, so this has a very high structural homology to dihydrofolate. Now the enzyme is not going to bind, or the binding for this is going to reduce and this is going to bind. So by the way, and because of that you have to, the synthesis of this will be reduced, so it will act, so this will act as a cancer drug. Okay, so the drug that you are taking is nothing but methotrexate. So the activity is by reducing the activity of this enzyme. So these are inhibitors. So for this to be effective, it should have a lower Km than this, right? Only then this will bind more effectively. If it's a competitive inhibition, I'll talk about the different kinds of inhibitions. But if these two are there, this is synthesized in the body. Now you are giving it from outside this. Why will this enzyme take your molecule and not its own molecule? It will take this only if this has a greater binding to this than this, right? And when will it have a greater binding? When the Km is low, right? So this is actually the enzyme is binding to this inhibitor. So you need to know the kinetics, or you need to know the various parameters. Okay, when you are designing a drug, you need to see how efficient these drug molecules are. And for knowing that, you need to know what is called enzyme inhibition kinetics. Now here is an example where the enzyme, the substrate or the inhibitor is binding directly to the enzyme. But there are also cases where the inhibitor can bind to the enzyme substrate complex. So there are different kinds of inhibition that I will talk about, but so this inhibitor can bind to enzyme or this inhibitor can bind to this, right? So this will give two complexes. Now that you have understood why it is important to look at enzyme kinetics, we will see how the equation for the enzyme inhibition kinetics is different from the enzyme kinetics. Okay. Now what is the total concentration of the enzyme? E0. Total E0 is how much? What is total E0? E plus ES. That's all? Sure? In this case, so if the inhibitor was not there, then it is E plus ES. When you have an inhibitor, some of the enzyme is forming this, some of the enzyme is also forming this, no? So your total concentration of enzyme is E plus ES plus EI plus ESI. So some of the enzyme is in the enzyme form, some of them is in the substrate form, some of them is in the enzyme inhibitor complex, and some of them is in ESI form. Now what will be the rate of enzymatic reaction? At the end of the day, what will be the rate of the product formation? So our main enzymatic product is this, right? T. So what will be my dP by dt or plus dP by dt? What will be the rate of my reaction? It will still be K2 into ES, right? Because only the enzyme substrate complex is the one that is forming the product. None of these reactions are forming the product, right? So these are all kind of side reactions, byproducts kind of thing. So not byproducts but side reactions. So only this is the reaction that is giving you the product. So at the end of the day, your reaction is still determined by K2 into ES, right? But now your overall enzyme concentration has changed. You previously, in the previous case, your E naught is equals to just E plus ES, right? And from there, I don't know, did anybody do the expression that I asked you to do? I didn't do the final derivation yesterday. I asked you to do, did anybody do it? So I asked you to just use this and then substitute there and then you will get it. So here it is a more complicated reaction, right? So if I have E plus S into S, what is my Ki? Suppose I have a equilibrium constant. By the way, is this going to be an equilibrium reaction or a one direction reaction? So whether it's an equilibrium or one direction will depend on whether it is a covalent modification or a non-covalent modification, right? So if it is a covalent modification, it is always one direction. You will not have an equilibrium. So there are inhibitors that are irreversible inhibitors. Okay, for example, penicillin. Penicillin is an irreversible inhibitor. Okay, aspirin molecules that you take, that's also an irreversible inhibitor that they do covalent modification of the enzyme. Right? So there the direction is only in the one direction. But what I am talking now is about reversible inhibitors which are non-covalently binding. For example, the example that I gave you, which is methotrexate binding to DHFR, right? So that is a reversible inhibitor. So you will have both equilibrium constants here. Okay, now can you tell me what is the equilibrium constant Ki? What will be my equilibrium constant? E into I by Ei, right? And what will be my equilibrium constant Ki prime? Es into I, because there is also I here. Okay, so these are the two equilibrium constants that we have, right? So what I am trying to do is, I am trying to show you how the inhibition kinetic, when there is an inhibitor, how does the enzyme inhibition differ from without the inhibitor? Okay, now coming back to this, E0 is equals to ES plus ESA. Now can you write these in terms of the equilibrium constants? So I am just defining two new parameters. This is just a definition. Alpha is equals to 1 plus concentration of I by Ki. Alpha prime is equals to 1 plus concentration of Es by Ki prime. Now, can you write this in terms of alpha? By the way, did you get what I am trying to do? What I am trying to do is, now I have two new reactions, right? So previously the rate of the reaction is still same, K2 into Es. Now in our previous case, we have derived an expression for Es using steady state approximation and did it. For that you have used this E is equals to E0 plus E0 is equals to E plus Es. But now that expression is no longer valid here, because this Es is not E naught minus E, but it is more complicated because the total enzyme is divided into 4 parts, right? Now for that I have taken the equilibrium constants Ki and Ki prime. Now because the rate is still the same, I want to write this E naught, because I want to derive an expression for Es in terms of E naught. Right, that is my ultimate aim. If you remember yesterday, that is what we did, Es in terms of E naught. So I want to derive this expression for Es because these are all temporary ones. We cannot calculate anything. Only thing that is constant is E0, right? To start with, you only know the enzyme concentration. So even if you see the yesterday's reaction, nu is equals to K2 E naught substrate concentration 0 by Km plus substrate concentration 0, right? So your rate of the reaction in this all are known, right? You know the rate, you can calculate the rate constant. E0 is the starting enzyme concentration, S0 is the starting substrate concentration, Km for a given reaction is constant, S0 is constant. So now I have something in this form. So that means I need to have everything in terms of either E0 or S0, right? So that is what I am trying to do. Now for that I have taken that E0 is equals to E plus Es plus Ei plus Esi, right? Now using these two definitions, alpha is equals to 1 plus I by Ki and alpha prime goes to 1 plus Ei by Ki, can you write this? E0 is equals to in terms of alpha and alpha prime? That is the question. Can I write it this way? E0 is equals to E alpha plus E alpha, Es alpha. If you want, you can cross check it. You can substitute this and these definitions, and whether I am getting that or not, one of you or few can you quickly check. So what I am trying to do is I am writing the E0 in terms of Es prime and alpha and alpha prime. That's all. Can one of you substitute, or can all of you substitute these expressions and see whether these two are matching or not? I'll give you 2 minutes. Just I have given you that expression. Just make sure that I'm not doing any mistake. Whether these two are same or not is what I want to confirm. The alphas are given. If you want alphas in Ki, the Ki's are given. So I want you to find out whether these two are coming out to be same or not. You do that. I'm just doing something else. Did anybody verify this? Did anybody get this or no? Nobody got it? What is alpha? Okay, so 1 plus I by Ki. What is Ki? E into I by Ei. So if you substitute E into I by Ei, II gets cancelled, this Ei will go up, right? Ei by I, 1 plus Ei by I. So E of 1 plus Ei by I. So E into 1 E, then so this will become E plus Ei, right? E alpha will become E plus Ei, Es alpha prime will become Es plus Es alpha, ESI, right? So you just have to substitute it, there is nothing that I did. So I made, just to make the life simple, I have kind of did everything, I have made this into a concise form, E alpha into Es alpha. Okay, so basically why I am doing this is because I want to finally have the value of Es so that I can substitute in the rate of the reaction. Okay, this is my rate of the reaction in the presence of inhibitor. Now can you tell me what will be the Michaelis-Menten equation look like when I so I already got the value of Es, right? So you have the Es, so can you substitute in this and tell me how does the equation look like? So in the presence of inhibitor, okay, K2, I am writing S but it should be S naught, okay. I am not doing a derivation, but you should be able to do that. So from this expression you can get Es in terms of E naught, Km, S, alpha and alpha prime. So once you substitute this Es here, you will get this one. Okay. Now that we have derived the mathematical form is only for you to show, for you to understand, but let us understand what is the physical significance of that, right? So you can see that the expression for this is a non-inhibited reaction, this is an inhibited reaction, right? You see there is a difference in the expression in terms of alpha and alpha prime. If you just convert this into your Lin-Weaver-Burke form, what is the Lin-Weaver-Burke form for the top one, non-inhibited reaction? One by mu is equals to Km by Vmax into 1 by S plus 1 by Vmax. And for an inhibited reaction, what is the Lin-Weaver-Burke plot for an inhibited reaction? 1 by nu is equals to Km alpha by Vmax, right? That the K2 into E, this is K2 into E naught is nothing but your Vmax, right? So Vmax into 1 by S plus alpha prime by Vmax. So as you can see, both this is the apparent, so both apparent Km and apparent Vmax, both of them have changed. So if you look at enzyme non-inhibited reaction, inhibited reaction, both the apparent Vmax value and the apparent Km value have changed. So in which cases do we have this is what we have to, we'll look at 3 different cases and how does this affect this particular expression is what we are going to see. Did you guys note this part? Okay. So there are different kinds of inhibitions: competitive, uncompetitive, non-competitive. Okay, so as I told you in the beginning, so first example was where your methotrexate was actually binding to the, in the place of dihydrofolate, right? The enzyme is DHFR, but the instead of the dihydrofolate, the methotrexate is binding. That means it is actually competing with the substrate. Now suppose let us take a simple, I am just putting this as an example of, okay, this is some enzyme, okay, I am just a rough diagram. Okay, now I have an enzyme and that binds to a substrate. Okay, now in the competitive inhibition, so this is a substrate, okay, this is a substrate. In the competitive inhibition, there is a new molecule which is inhibitor that kind of competes with this one. So that means it will have something like this. So this is not a substrate molecule, but this is an inhibitor molecule. That means it will bind at the same place as your enzyme, substrate, okay. So this is called competitive inhibition. So in this case, what is changing? Will my Km change or Vmax change? So if suppose, so I have a certain, so finally this is the one that is going to give me product, right? This is the one that is going to give me a product. Okay. Now you have, instead of this substrate, there is a new molecule which is inhibitor that is binding at the same place as enzyme, and so this is kind of competing with the substrate, right? So what, for the overall enzyme kinetics, what will change? The Km will change or Vmax will change? Vmax will change. Vmax is basically coming from this particular enzyme substrate complex, right? Okay, I will put it in a simpler way for you to understand. So this is your final reaction, right? Now in the competitive inhibition, what is happening? The enzyme is reacting with the substrate, and with an inhibitor it is forming this EI, right? It is in this equilibrium. So it is not affecting this ES, it is only forming a new complex. So the substrate, so basically you need more amount of substrate because your substrate is being competed by inhibitor. Now suppose if you have more amount of substrate, then slowly it will also kind of go back to its original position. So that means, so the your final Vmax is determined by what? Final Vmax is determined by the formation of ES, right? But forming the ES is becoming slow because the ES formation is being inhibited by a new enzyme, right? So your ES is still forming, but the rate of forming this ES has reduced because you have a new inhibitor that is competing with the substrate. So in this case, your Km is the one that is going to be affected, but your ES, because your Vmax is not going to be affected because you are still forming the ES. Okay, so in the competitive inhibition, your Km is going to be increased, whereas Vmax is not going to change. Okay. Now let us see what is uncompetitive inhibition. In uncompetitive inhibition, you have your enzyme that is binding to a substrate. Okay, this is a substrate. Now upon binding to the substrate, it creates a new active site where your inhibitor will bind. So this is your inhibitor, this is your substrate. So in uncompetitive inhibition, you have a new substrate, you have an enzyme substrate complex, but because of an enzyme substrate complex, a new site is bound, and that is actually where your inhibitor binds. So because of this, both Km will decrease and Vmax will also decrease. And why is that? So this I is binding only to the ES complex. That means it is binding here, right? It is binding here. Now it forms ESI. So this is not going to give me product. Only ES is going to give me product. Now because some of the enzyme substrate ES is forming ESI, the reaction will be directed more towards this. That means you will require less and less substrate. So that is why your Km will decrease. But because this is not giving you the product, only this is going to give you product, and so because the Vm will also decrease. Okay, so in a non-competitive, in a uncompetitive inhibition, both Km will decrease and Vmax will decrease. This is surprising because Km should generally increase, right? When you have an inhibitor, Km for the substrate should, this is a substrate Km, okay. But because some of the ES is kind of forming this ESI, the concentration of this is decreasing. So you will have more and more, the reaction is kind of governed towards this direction. So you will require less and less substrate. So your Km will decrease. Okay. In case of non-competitive inhibition, so you have a substrate that is binding, and enzyme, the inhibitor, it binds to a different region, and this can bind to both enzyme or enzyme substrate complex in both the cases. So in this case, your Km, because it is not affecting this, so your Km is not going to change, whereas your Vmax is going to decrease. So you have three different modes of inhibition: competitive, uncompetitive, non-competitive. I'll once you note it down, I'll again briefly tell you what I have done here. Okay, to again put it in a simpler way, what we were discussing is the inhibition kinetics. Now the inhibitor, it can have different modes of action. As I told you, one example, right, where methotrexate will kind of compete with the dihydrofolate. That is basically, this is your dihydrofolate, this is your methotrexate. Now this is supposed to bind and give this and give this. This is the original pathway. Now you are adding a new molecule here which is competing with this and forming a new complex, and this is not going to give you product. Competitive inhibition means your inhibitor is going to compete with the substrate for the same space, for the same active site. Okay, you have one active site, this is the one that will actually give you product. Now if you add inhibitor, the inhibitor is going to compete, and by the way, this is all reversible, so non-covalent interactions, right? So it is going to compete with this substrate and it is going to bind. Now once this binds, this is not going to go into product, only this is going to go into product. So this is called competitive inhibition. So competitive inhibition, because this is still forming, right? So if you increase the substrate concentration more and more, then finally you will have enough of this, so you will have your product. So the Vmax is not going to change, but your Km will change because you have to add more and more of S to compete with this. Okay, this is called competitive inhibition. Uncompetitive inhibition means you have, so the inhibitor will not react with the enzyme. The inhibitor will not react with the enzyme. The inhibitor will react only with the enzyme substrate complex. So once this enzyme substrate complex forms, it creates a new site where the inhibitor will bind. Now once this inhibitor binds, this will form ESI, and this is not going to give you product. But because some of the ES is going into ESI, the concentration of ES will decrease. If the concentration of ES decreases, the reaction proceeds in this direction. That means you will require less and less of S. So that means your Km will decrease. Now because your total overall concentration of ES is going to reduce, so your Vmax is going to change because this is not going to give you the product. Now non-competitive inhibition means your inhibitor can bind to either E or ES, both these things, right? So in that case, if it is binding to both the cases, because this is binding at a very different site than the substrate, it is not going to affect your Km, because Km is only affected by the substrate binding, but it will change the Vmax. Okay, so these are the common. So just by doing the kinetics, you can determine the mode of action. And why is it important to know the mode of action? So based on the mode of action, you can change the dosages, you can change the understand the activity of it. So just by determining the kinetics, you can have a mode of action. Now this is the Lineweaver-Burke plot for non-inhibited reaction and inhibitor reaction. Now on the same plot, can you draw? I'll draw for the first one, remaining two you draw. So suppose I have so this is my Michaelis-Menten curve. This is this is my Lineweaver-Burke plot. 1 by mu 1 by S. What is this value? What is this value? 1 by V max. What is the slope? Km by V max, right? This is basically Lineweaver-Burke plot. Now, if I have a competitive inhibition, which is this case, if I have a competitive inhibition, what is changing? Is my Vmax changing? No. So, how will the line look like if I, this is a non-inhibited reaction, right? Now, how will that look compared to this? How, if I plot for an inhibited reaction, if I plot a Lineweaver-Burke plot, how will that look? Tell me, it is still a linear curve? Without intercept, that means 0. The Vmax is not changing as I never said it is 0. So, intercept will be same. What is changing? Okay, so Km will affect what? Km will affect slope. Now, is my slope going to increase or decrease? Because Km is increasing, so your slope will increase. So, for a competitive inhibition, my reaction will look like, so the intercept will be same, but it will have a higher slope, right? Agreed? Now, for non-competitive, can you draw for a non-competitive, how will it look like? And these two will change by same value. These two will change by same value. Line? I didn't understand. Origin, but I never said Vmax 0, no? If a line will start from 0 when the intercept is 0. But Vmax, if Vmax is 0, then reaction is not proceeding. What do you mean by Vmax 0? Vmax 0 means that maximal rate itself is 0. That means there is no enzyme catalysis, no? Intercept will decrease. What is intercept? 1 by Vmax. If Vmax is decreasing, 1 by Vmax will increase, no? So, intercept will increase and slope, because both are changing, no? Km is changing, Vmax is changing, and both are changing by same value. So, slope will remain same, Km by Vmax. If this is changing by 2 times, that is changing by 2 times, both are changing by 2 times, then the ratio will remain same, right? So, Km by Vmax will remain constant. So, intercept will increase, slope will remain same. So, how will it look like on this? It will be a parallel line. Slope same is parallel, right? Slope same, right? But the intercept has increased. This is for your uncompetitive inhibition. And for non-competitive inhibition, what will happen for a non-competitive inhibition? Vmax is increasing or decreasing? Vmax is decreasing. So, intercept will increase. Okay. And what about the slope? Slope will decrease. Why will it decrease? Km same. Vmax what happened? Vmax has decreased. In the slope, Vmax is in numerator or denominator? So, if this is decreasing, what will happen to the slope? Increase. So, you will have an increased intercept as well as increased slope, right? So, for something like so, you will have an increased intercept as well as increased slope, something like this, and they will meet at some. So, you will have an increased slope because Km by Vmax is changing, Km is remaining constant, Vmax is decreasing. If this is decreasing, the slope will change because your slope the slope is in Vmax is in denominator. Now Vmax is decreasing, so this will also increase, right? So this is for your non-competitive inhibition. Okay. So just by doing kinetics, that means again we are doing a simple experiment. What is the experiment that you are doing? Now without the inhibitor, you determine the rate of the reaction at different substrate concentration, right? Nu and S. So once you plot 1 by mu, 1 by S. So without the inhibitor, you calculate the rate of the reaction with substrate concentration. Now add the inhibitor and again calculate the rate of the reaction with the substrate concentration. Depending on what kind of curve you are getting, you can tell whether it is a competitive, whether it is a uncompetitive, or whether it is a non-competitive, right? And all these will have different mechanism of action, right? So for example, competitive. Competitive means what? If suppose you determine that it is a competitive inhibition, then if you want to reduce the effect of inhibitor, you just have to increase the substrate concentration, right? At some point it will change, but these two will not have any effect on substrate. So you can determine the mechanism of action. So you have a drug molecule. Here I am saying inhibitor, but let us take it as a drug molecule. Whether the drug is binding to the same place as a substrate, or whether the drug is binding after the substrate is binding, or whether it is binding to a different place than where the substrate is binding, that entire information you can get just by doing a kinetics, right? Because based on the shape of the curve, whether the slope is remaining constant or intercept is remaining constant or both are changing, based on that you can determine the mode of action, mechanism of action. Now once you know the mechanism of action, you can improve the drug efficiency, right? So if it is a non-competitive or competitive, you can change the molecule or fine tune the molecule so that it will inhibit it in a better way. So just by understanding the kinetics of enzyme inhibition, you can determine the mechanism of action, whether it is binding in place of substrate, whether it is binding after substrate is binding, or whether it is binding at a different place. So based on that, a simple this can do this, right? Now I will give you a simple homework kind of thing. So this is your Michaelis-Menten curve, right? This is your simple Michaelis-Menten curve. What we did is for a Lineweaver-Burke plot, right? Can you draw for the three inhibition modes: competitive inhibition, uncompetitive inhibition, and non-competitive inhibition? If suppose this is a non-inhibited reaction compared to this, how will the Michaelis-Menten curve change? That we did it for an easier thing, which is basically a Lineweaver-Burke plot. Now this is slightly more complex, and that you can do it as a homework. Just by looking at the kinetics of a reaction, you can determine the mechanism of action, right, of the inhibitor. Now this is very, very, very important when you are actually developing a drug, to understand how much dose. So for example, you take Dolo 650, right? You all take 650 mg. How did we come up with this random number of 650 mg, right? Or you take some drugs, you take 5 mg, you take 10 mg. So these things will depend on how much, these are all inhibitors, right? How much inhibitor, that is inhibitor concentration, right? So and also how long they are acting. And so in medicinal chemistry, there is a term called IC50, okay, which is basically giving you at what concentration the activity is 50%, okay. So you have to optimize various other things like whether it is toxic or not toxic or something, but you should also determine at what concentrations will the drug be active, no? So for calculating the concentrations at which the drug is active, you need to know all this kinetics of it. You need to calculate the kinetic parameters. You need to know the mechanism of action. So in those cases, enzyme inhibition kinetics is very, very important. And what we did today is to mathematically derive how the Michaelis-Menten kinetics of enzyme inhibition is different from non-inhibition, and what are the different modes of inhibition, and if you convert these different modes of inhibition to Lineweaver-Burke plot, how does it vary? So just by doing a simple, this is a very easy experiment to do. You determine the rate of the reaction by adding different substrate concentrations in the presence of enzyme, in the absence of enzyme, and calculate this, and based on the kind of nature of the curve that you are getting, you can actually determine the mechanism of action or mode of action, and this is very, very important if you are doing a drug design. So I'll stop this part of enzyme kinetics or enzyme inhibition kinetics here. Any questions on enzyme kinetics or enzyme inhibition kinetics? No? Okay.
SwayamPrabha. Digital India. Educated India.